So, as we wrap up the last part of chapter 8, let's get into an example problem and see how this data is actually presented. Because oftentimes, you're just given the summary statistics of a study and you're asked to do some sort of analysis. So, let me present a story problem for you. And for some reason, your book loves talking about beer and blood alcohol. I don't know what that says about you or the audience that they're trying to direct to, but let's see what this says. So, how well does the number of beers a person drinks predict his or her blood alcohol content? 16 volunteers with an initial BAC or blood alcohol content of 0 drank a randomly assigned number of cans of beer. 30 minutes later, a police officer measured their BAC. Least squares regression was performed on the data, a scatter plot with the regression line added, a residual plot, and some computer output from the regression are shown below. So this, oftentimes, and especially the AP test, they love presenting this information. So let's kind of go through what it's trying to tell you and then look at the scatter plot, do our basic analysis, and then see where we get. So when it says dependent variable, that is saying our Y variable. So we would say BAC hat. Our R squared is 80%. That gives us our variability. In our case, we're going to ignore the adjusted. That means something. When they say S, that means the standard deviation of our residuals. So standard deviation of residuals. And if you remember, we said S sub E is how well our model or how well our data fits our model, how much variation. That's for later on. I mean, it means a thing, 16 minus 2. You can see that there's 16 people. Degrees of freedom will help. Again, that also will help us with the T ratio, but that's all the way in chapter 27 when we round the corner. What I want you to look at is the variables and the coefficients. So it says constant. That's our y-intercept, our b naught. And beers, which is our explanatory variable, is our slope. So that's b1. So we have all of these pieces of information if you know where to look. So let's flip it. Let's see what the scatter plot is and do our basic interpretation. So if we are looking at this, note, labels. We have our line of best fit and we have our 16 data points. As the number of beers increases, the blood alcohol content also increases. So we see a strong, positive, linear model. As the number of beers increases, blood alcohol tends to increase. Note, again, squishy words. We are not precise here. We're just trying to describe approximately. Now, we also look at the residual plot for beers, and we see that there's no pattern in the residuals. We don't want to see anything, so we are good to go if we don't. Also note, in our scatter plot, the majority of data values fall between -3 and +3. So if we're pulling all this out, and this is just a reference for you guys, as you saw, BAC was our response variable. We have our R squared, we have our S sub E, we have our y-intercept, our explanatory variable, our slope, and then everything else saved for chapter 27. What we will get is the equation. So we have our predicted blood alcohol content, or BAC hat, is equal to -0.0127, which is our y-intercept, and we have 0.017964 times the number of drinks. And that is our slope, all just pulled from the computer output. Now, whenever we're reporting out our least square regression analysis, we are also going to interpret the slope. So for every additional beer consumed, the model predicts a BAC increase of about 0.018 BAC. Also, we were reporting out the R squared, so 80% of the variability in blood alcohol content is accounted for by the model. And then we would also finish out by saying a linear model does seem appropriate for this data. We can see that there's not a whole lot of sway from our standard deviation of our residuals. Also do note, the residuals are between -0.03 and 0.03, as I showed before. Here is where our residual plot is. So except for this guy, someone drinking 9 beers, on average, predictions That's what the standard deviation of the residual. Remember, residual is the error from our actual values to our prediction. On average, predictions of BAC using this model would be off by about 0.02 for 16 people in the study. Now, if you think about that, given a legal limit for most states in drinking is 0.08, that error may be too much. And that might be too much for all of us to consider. So we're just going to finish up here and talk about some assumptions and conditions that we have to verify in order to justify using a least square regression model. So first thing, when you're doing this type of analysis, we need to be dealing with the quantitative variable condition. Regression can only be done on two quantitative variables and not two categorical variables. So you must check and report out the quantitative condition. Similarly, the straight enough condition. A linear model describes a relationship between the variables that is linear. If the data is not linear, aka curvilinear, a linear model is not appropriate. And it seems redundant, but you have to say that a linear model is appropriate. A scatter plot, remember, draw a picture, will indicate that the assumption is reasonable. So that's what you need to provide. If the data is not linear, you stop, you're done. Some nonlinear relationships can be saved by re-expressing the data to make the scatter plot more linear. We will revisit that in chapter 10. Continuing on. It's a good idea to check linearity again after computing the regression model when we can examine the residuals for any pattern that may have been missed from the scatter plot. So sometimes it seems kind of backwards, but we actually run the linear regression and then we check for linearity by looking at the residual plot. And then we get to this equal variance assumption. So we have to check that residual plot and the standard deviation of the residuals to summarize the scatter. The residuals should have the same spread throughout the domain of the predictor variable. It should be roughly the same. Check for changes in the spread of the residual scatter plot. If you see something happening, that's like, does the plot thicken? And we'll get more into that in chapter 9. So ironically, we must run the model first to be completely certain the model is worth running in the first place. I know, it seems backwards. Last bit, outlier condition. Watch out for outliers. Outlying points can dramatically change the correlation and the regression model. Oftentimes we'll say that they have leverage over the situation, or maybe they have influence over the situation. In extreme cases, outliers can even change the direction of the slope, completely misinforming the reader about the relationship between the variables. So watch out for influential, and points of leverage. And if you're wondering, we haven't talked about that yet, that's because that is in chapter 9. So we will add more to this analysis. So let's just do a quick reality check. Is the regression reasonable? Statistics do not come from out of the blue. Statistics are based on data. Data are collected by people. The results of a statistical analysis should make sense and be logical. If the results are surprising, then either you've made a new discovery and added to the human lexicon about the world, or more likely, our analysis is wrong. So when you perform a regression, think about the slope and intercept and consider, does this make sense? So CCRs, if you Google this, these are words of advice. Covenants, contracts, things to keep in mind of. First, don't fit a straight line to a nonlinear relationship. If you see that there's a curve, it doesn't make sense to add or do a linear regression. We're done. We stop there. If you see extraordinary points, so that means y values that appear far away from the linear pattern, look at those. Remember what we've done before with outliers. We first report out with, and then we take it out of the data set, and then we do an analysis again. Be careful. It's so tempting, but do not extrapolate beyond the data. Think that giant rat that we saw earlier. The linear model may no longer hold outside of the range of the data. Do not infer causality. that the predictor variable causes the response variable to change simply because there is a good model for a relationship. Note, association is not causation. I'm not trying to make you sick. I need you to know this. Just because we find an association or the R is very, very close to 1 does not mean that one causes the other. In order to determine causation, we need to have a controlled experiment, which most of the time we aren't in charge of. Also, R squared is a valuable indicator and must be included in any regression. But look at the entirety of the data in the model. Do not judge a model solely based on R squared alone. So maybe R squared is really high. Maybe it's really close to 100%, which means that the model accounts for all of the variation in the data. Or maybe it's close to 0. Be careful with what this means. So outliers and influential observations. Like I said before, an outlier is an observation that lies outside the overall pattern. Points that are outliers in the y direction, but not in the x direction of a scatter plot have large residuals. Outliers in the x direction may have undue influence on the model and thus not have large residuals, but really direct, let's say, 1 point way out there. It's going to make our line fit closer to it. An observation is influential if removing it would significantly change the results. Points that are outliers in the x direction of a scatter plot are often influential for the least squares regression line. Again, more about that in chapter 9. So just in conclusion, to wrap this all up, put a nice little bow on it. A regression line is a straight line that describes how a response variable, the y, changes as the explanatory variable x changes. You can use a regression line to predict the y value for any value of x by substituting the x into the equation of a line. Think y hat equals b1 plus b0 plus b1 x. We are plugging in the x to see what the y is. The slope, which we are calling b sub 1 of a regression line, is the rate at which the predicted response changes along the line as the x variable increases. The y-intercept of a regression line is the predicted response when the explanatory variable is 0. This prediction is of no statistical use unless x can actually take on values near 0. And we put that in there to say, like, if we're talking about age, you could technically be 0 age, but if you're looking at what does that mean when a baby is born and you have a negative number, it maybe not make a whole lot of sense. Likewise, we made it a point before, but let's just hit that again. Avoid extrapolation, trying to make predictions past the actual collection that we have. Do not use the model for the values of the predictor variable outside the range of the data from which the line was calculated. And the most common method of fitting a line to a scatter plot is least squares. The least squares regression line, or LSRL, is the straight line y equals b0 plus b1x that minimizes the sum of the squares of the vertical distance of the observed points from the line. Think the Desmos activity that was in the notes in part 1. And the least squares regression line of y on x is the line with the slope b1. Note, our slope comes from our correlation coefficient and then our standard deviation of our y variable divided by the standard deviation of our x variable. And the y-intercept uses the averages of those two, y bar minus b1 times x bar. This always passes through the point x bar comma y bar, or the average of the x value and the average of the y value will always be on our line of best fit. You can examine a fit of regression line by studying the residuals. Remember, residuals is the difference in the actual output minus our predicted output. How off was our model? Be on the lookout for points with unusually large residuals, nonlinear patterns, and uneven variation about the residual y equals 0 in the residual plot. Remember, we don't want to see a pattern when we're looking at the residual plot. The standard deviation of the residuals, how much variation there are in our error measurements. The measures the average size of prediction errors when using the regression line. Our R squared, or coefficient of determination, is the fraction or the percent of the variation in one variable that is accounted for by our model on the other variable. And most of all, be careful not to include that there is a cause and effect relationship between two variables just because they are strongly associated. Remember, correlation does not equal causation. So that wraps it up. That is chapter 8 in a nutshell. We're going to do a couple more practice problems in class. We're going to review, and then we're going to test on chapter 7 and chapter 8. Thanks for sticking with me, Falcons. See you guys in the next one.